Okay, let's have a look at another example, example 3a. So it has two questions, A and B. Figure 3.7, which is this, shows the composite rod structure consisting of aluminium rod AB. So this gray color is AB from here to here. This is AB rod. Is bonded to the brass rod BD. So this is B to D here. So this is BD. Is subjected to torsional loading. So this is the direction of the torsional load, which is torque at A and torque at B, respectively at 700 Newton meter at A, and at point B the torque is 1500 Newton meter. Rod AB is a solid rod, while rod BD consists of two portions, which is solid rod for portion BC, this is solid at around from B to C, and hollow rod for portion CD. So from here to here there is a inner empty space inside the rod BD from C to D, with the cross section as shown for the structure. So the cross section, this is the cross section for BCD, and this is the cross section for AB. Determine 1. The absolute maximum shear stress in segment AB. So what is the value of shear AB maximum, and the second, what is the value of shear maximum at portion BC, and also shear maximum at portion CD. So to solve this problem, you need to divide the whole structure of shaft into several part of segment. Divide shaft into segment. And then use free body diagram to determine the internal torque. To determine the internal torque. So let's say this is a torque A, this is torque B. So between A and B there is a torque in which that we call it as internal torque, TAB. And let's say this is torque B, which twists the rod B to D, but there is an internal torque here, we call it torque BC, internal torque BC, and also here there is an internal torque, we call it torque CD. Okay, so there are torque A, torque B, and there are also internal torque AB, internal torque BC, and internal torque CD. Okay, so when you determine this each internal torque at AB, BC, and CD, you can determine this shear maximum by using the equation. Shear maximum is equal to torque times C over J. So let's say if the shear maximum that you want to determine is at rod AB, so shear maximum AB is equal to torque at internal torque at AB times by the value of radius C at AB divided by the J of AB. So what you have to determine, you have to find first this one and this one. This one you already know because you have the value of the cross section here, here and here. Okay, so let's change this slide into an empty slide so that we can do the calculation. Okay, as said previously, the shear maximum, let's say at point B, AB, torque AB is equal to torque, internal torque AB times CAB over JAB. So JAB is equal to, so the equation is 1 over 2 times pi times C to the power of 4, which is equal to 1 over 2 times pi times 0.03 over 2, this is a diameter, over 2, and then times to the power of 4. So you will get, the answer is 7.952 times 10 to the power of minus 8 M4. And you can calculate also JBC, because later you want to find what is the value of shear BC maximum. So it is the same, so 1 over 2 pi 0.06 over 2 times the power of 4, you will get 1.272 times 10 to the power of minus 6 M4. And JCD 1 over 2 pi 0.06 over 2 to the power of 4 minus, because JCD is hollow shaft, so this is the equation C2 to the power of 4 minus C1, this is C1 to the power of 4, so you will get 1.021 times 10 to the power of minus 6 M to the power of 4, so you get J. And then you can put okay, so now you know this value and you know this value, but you don't know this value yet. So find internal torque AB, internal torque BC, and internal torque CD. So to find this, you have to divide the whole shaft into several sections. So section 1. So between rod A and B, this is, let's say this is rod A and B, this is point B, this is point A. So at point A, you twist the torque upward like this into the clockwise, and then the value is that you give is 700 Newton meter. So when you twist the rod at point A clockwise, the other end will resist the direction in and opposite direction. So if this going up, this will go down. Okay, so the you have to find the equilibrium in order to find what is the value of internal torque at AB. You have to use the equilibrium equation. So in this case, you can use the summation of moment. Let's say if you consider this as y direction, so it should be equal to 0. So the summation of moment at y direction is equal to 0 is TA, because if you consider this as positive, going up is positive, so TA is minus TAB, because the direction is going downward, and it should be equal to 0. So TA is 700 Newton meter minus TAB equal to 0. So TAB is equal to 700 Newton meter. So now you know what is the internal torque at point at shaft AB. So you know now. Also, so you can put the shear maximum at rod AB is equal to torque AB times CAB over JAB. So this is 700 times C. What is the value of C? C is equal to 0.03 over 2 divided by JAB that we have calculated is this one, 7.952 times 10 to the power of minus 8 m4. So the final answer is 132.04 megapascal. So this is the first question, A1. So we go to A2. A2, shear maximum at point BC. Same equation, so it is equal to torque at point BC times C for rod BC over JBC. Torque is equal to that we have calculated, or we have calculated torque for point BC yet. So the segment for rod BC is, this is your AB, this is point B, this is point A. So your rod BC is a little bit bigger. So this is BC. So let's say this is point BC. So so at point A, just now it is the same. It is the torque that we apply is clockwise, and then because so at point B here also we apply torque B, which is equal to 1,500, and this one is 7,700. So you give two torque at A and B, both at 700 and 1,500, and then at point between B and C, there are a resisting torque which is in opposite direction of A and B, so this is known as torque BC. So it is equal to the summation of moment in y direction should equal to 0, and this is TA plus TB minus TBC, because A and B is going in clockwise and this one is anti-clockwise, so it is different direction, so that's why plus and minus play the role. So TBC is equal to TAB TA plus TB, so 700 plus 1500, which is equal to 2200 Newton meter. So the value of TBC is 2200 Newton meter times CBC is 0.06 over 2, divide by JBC. JBC is this value, 1.272 times 10 to the power of minus 6 M4. So you get the shear maximum at point BC is 51.87 MPa. Okay, and then this is solution for A2 and the solution for A3. So same, shear at B, no, it's not BC, CD maximum is equal to torque CD times CCD over JCD. So torque CD, you can draw like this, the free body diagram. This is AB, this is BC, and then BC and CD is connected. So let's say this is A, this is B, this is C, and this is D. However, here from D to C, it is hollow. Okay, so you have given a TA, which is equal to 700, and then you have given TB, which is equal to 1500, and there is a resisting torque at the end. This is point D at the end of the shaft, which is TCD. So TCD, the summation of moment in y direction is equal to 0, so it is TA plus TB minus TCD equal to 0. So TCD is 2200 Newton meter, so same as TBC. Okay, so TCD is 2200 times CCD. So what is CCD? CCD is 0.06, because this is the auto diameter, over 2, divide by JCD. So JCD is hollow, so the equation is like this. Okay, so we have calculated what is JCD, 1.02 times 10 to the power of minus 6 M4, and you get 64.64 MPa. I think this is 1.0121. Okay, so that is question A for this problem.